wait for a few more minutes. In the meanwhile, I have a lot of food to eat. So thank you very much for coming. I'm very happy today to present you Ahmad Mansour. Ahmad joined KAUST in September 2014, and now he's defending his master thesis. Before coming to KAUST, he was an undergraduate at the Bursty Institute of Technology and Science in India, one of the top engineering schools. And he was also a software engineer at Yahoo, Bangalore. He has a lot of collaborators. Among them, he's collaborated closely with the Qatar QCRI Institute. The work that you will see today has been submitted to KDD. This is a top conference in data mining. We are still waiting for the results. They are in 2 days from now. Be accepted. Ahmad has also filed a patent based on this work. He has already been accepted for PhD in Stony Brook University. He will be working with Professor Agoglu, who is a collaborator of Christos Faloutsos, and this is a top team in knowledge extraction from graphs. So,
thank you for coming. So, if you could summarize this talk in just one sentence, what we're trying to do is answer this question. How can you compete in the attention economy? So, what is the attention economy? So, like any other economy, it has producers and consumers. But the difference in this case is that the product that is being sold is information or entertainment, and the currency is attention. So previously, the attention economy was sort of a monopoly. Production was controlled by traditional media, but now with the onset of online social networks, what you have is that everyone is now a producer. So the economy has been democratized. So what is common among all of these social network or social media platforms? And the common thing among them is their mechanism of information exchange. How does this happen? This happens, so production happens via broadcast in all of them, and consumption happens via timelines. Okay, so I'll introduce some terminology using the example of Twitter, but this works, or it can be generalized to any social network with broadcast and timelines. So in the case of Twitter, you have a producer, and the producer produces a bunch of posts. And how does the production happen? The producer takes a number of actions at particular times, and these actions are instantly broadcast to all the producer's followers, and they appear on the timelines of the followers. What is a timeline? A timeline is nothing but an arrangement of posts, and in the case of Twitter and Instagram and Vine, the sequence is reverse chronologically ordered. So throughout the presentation, when I refer to tweets, what I mean is a post on a timeline. So what gives rise to competition in this scenario? So competition arises from two factors. The first is the fact that everyone is a producer, so there's a lot of information being produced in the network. The second is the fact that consumers exhibit no restraint. So what this means is on Twitter and Facebook, people don't limit the number of friends or the number of people they follow. And this gives rise to information overload. And a consequence of information overload is that timelines are only consumed partially from the top downwards. So naturally what happens in this case is there is competition for the higher slots in timelines. So what are the problems that this gives rise to for you as a producer? So as a producer, you have different friends. These friends log in at different times, and each of these friends also follow a bunch of different users. So your competition is different for each friend. But you are restricted to broadcast. So this is not like email where you can time your email in a way that the recipient is going to read it. So you're restricted to broadcast, and you need to balance between all your friends. So this gives rise to the timing problem. So there is a naive solution to the timing problem, and that is to flood. You can post on Facebook once every second or every minute, and this is going to guarantee attention from all your friends, right? But the problem that comes here is irritation. So you know that people get irritated, and I'll discuss this in detail soon. So you need to control the frequency of your posts so that you don't irritate people. But at the same time, you want your posts to be read. And this is what we call the frequency problem. Trying to solve these problems is what leads to the contributions of this work. So the contributions are in three parts. So because this is the first time this problem is being attempted, is being solved, we need to scientifically motivate the problem. Okay, so the first part, we look at the factors influencing attention, and we identify three factors. One of them is something that has never been quantified before, and so we use real data from Twitter, and we study the factors that influence attention. Once we have these factors in hand, we need to go and somehow link the behavioral factors with schedules and attention. And we need to do this formally in a way that we can go and solve later. And so this is the second part of the presentation. And finally, we take our formulation and apply it to Twitter, the data from Twitter, to see what sort of insight can we gain from our formulation. So now, I'll move on to the factors that influence attention. The first factor, the way this factor affects attention is, so with increasing depth in the timeline, the attention that a post can receive is going to decrease. So this is something that was initially observed in an eye tracking study. So they actually attached these glasses onto users' eyes, and they tracked where they were looking while using Twitter. And they observed that, okay, people don't consume their timelines completely. But just last year, a team did a very large-scale study on data from Twitter, and they showed that they used retweets as a proxy for attention. So, and they showed that the probability of being retweeted, it decreases monotonically with depth in the timeline. And this is the observation that we adopt. The next factor is bursty circadian rhythms. So there are two parts to this. And basically what we are asking is, in microblogs, which is our scenario, is do we observe this kind of behavior? So you have time on the x-axis and the day of the week on the y-axis. So do humans act in bursts? So what I mean is there a long period of inactivity followed by a period of activity, and then again a long period of inactivity? And the second question we want to ask is, are these activity times periodic across days? And so this has been observed in a bunch of scenarios before, but we go and validate whether this exists in microblogs. How do we do this? So what we do is we take a data set called ViboScope, which is, Vibo is the Chinese Twitter, and we plot the distribution of time between two consecutive tweets by the same author. And you can see that this distribution follows a pattern which is composed of two sub-patterns. The first sub-pattern is that it follows a power law curve, and this power law curve has been observed to arise from bursty behavior in scenarios like email and blogging. Another pattern that you can see is that there are periodic deviations from this power law curve, and these deviations happen at 24-hour intervals. So where do these deviations come from? And they have been observed to come from circadian rhythms. And by looking at this distribution, we validate that Bursty circadian rhythms exist on microblogs. So coming to our the phenomenon that we introduce here for the first time is monotony aversion. So what we are trying to say is that if there are tweets by the same author consecutively in a timeline, it's going to irritate users, and this is going to negatively affect the attention that they receive. This has been observed in, so I've selected 4 scenarios. The first was an eye tracking study again, where they showed that consecutive tweets, each of the consecutive tweets receives lesser attention in the timeline. There were also small scale surveys on Twitter and Facebook, and interestingly, in the survey on Twitter, the users reported that they unfollow users who have burst tweets, regardless of the content of the tweet. So it doesn't matter what you say if you're going to say it in bursts. And finally, Facebook has a patent on something called diversity enforcement in a timeline. So if they see 2 posts on a Facebook timeline which are by the same author, they artificially push them apart. And so the question that we ask is why? So why do people try to solve this problem? And does this problem actually exist? So these are all small-scale surveys. Can we design an experiment on big data? So before we go to the experiment, let me introduce some definitions. So first is a timeline, which is a reverse chronological sequence of posts. Each post on the timeline has an author. So in this case, I've marked the author of, I've marked the post by P in red. Then you can talk about something called a cluster, which is nothing but a consecutive bunch of posts by the same author. So the cluster has an author and the cluster has a size. And then you can look at each tweet, you can look at its position in the cluster. So the first tweet in the cluster is at position 1 and it increases downwards. And you can also look at, was this tweet reacted to? So in the case of Twitter, was it retweeted or was it replied to? And in the case of Facebook, you can think of was it liked? Okay, this is our proxy for attention. So now that we have these definitions, what we can do is, for every user, given a data set, you can deconstruct the user's timeline. And for any tweet on the user's timeline, you can calculate the size of its cluster. You can also calculate its cluster position. And you can also look at was it retweeted or not. And once you have these, once you've calculated, observed these, you can go and calculate what is the probability that you get retweeted given the cluster size. So in this case, you can see that there are 3 tweets from a cluster size of 1, and only 2 have been retweeted. So that's, you get the conditional probability 2 by 3. Okay. So now we take a data set and we increase the cluster size and we look at the retweet probability. And what we observe is that the probability of retweeting decreases with increasing cluster size. And so the decrease is consistent for cluster sizes of 1, 2, 3, and then there is a bit of noise. So what this confirms is that there is some effect on the cluster size on attention, and it is a negative effect. What we also observe is that this decrease is statistically significant, so it couldn't have come from chance. Okay. So now we validated the existence of irritation from a Twitter data set. A follow-up question is, if you look at a single cluster of tweets, can tweets lower in the cluster affect the attention of the ones above? So what I'm saying is, can I create a cluster of 100 posts and still be confident that the first post in the cluster gets the same attention? Okay, so it turns out that, we're actually talking about hypotheses of consumption. How do people consume tweets? Do they consume tweets independently from the top downwards, or do they look at tweets in chunks and this affects their attention? So there was a paper back in 2011 where they observed that consumption was in chunks, and there was a recent paper where they're talking about advertising in a stream, where they assume that consumption is independent. So you can see that the research community is not decided on this yet. So can we go and validate these hypotheses on data? So we can. And the experiment that we perform is, we again look at the probability of reaction, which is a repeat or a reply, given the cluster size, but we also condition on the cluster position. And the cluster position of the tweet. And what we do is we fix the position, and then we increase the cluster size. And if the consumption was independent, what you would expect is that the retweet probability should not be affected. But it turns out that it is. So even for a tweet at position 1, if you increase the size of the cluster, it's going to reduce the probability of it being retweeted. So what this confirms is that people consume tweets in chunks, and that a tweet lower on the timeline can affect the attention of a tweet above. So this is all. This forms the motivation for our formalization. So now we need to go and formalize the problem in a concrete way. And how we do this is we do this in two parts. So we need to find a way to take a schedule and a social network, which is what we have, and link it to what each of your followers view in the timeline. And we do this via a process, a model of timeline information exchange. And then we need to go from the timeline to some metric of attention, which is what we do via attention potential. So now let's talk about the information exchange process. So you have a social network. Let's say you have a producer who is a blogger, and the blogger has n posts that the blogger wants to post every day. What you do is you divide your slot, your day into a certain number of time slots. So you discretize time, and you broadcast a certain number of posts in each time slot. And this is what I've shown here. So you also know that each of your users logs in at a particular time slot every day, and this is periodic. And this comes from our experiment on Bursty Circadian rhythms. So we have these parameters in hand. You can also observe. So here you have both of these users follow you and another competitor. Let's say it's a competing blogger. So you can also go and look at what is the schedule of your competitors. And I call it an aggregate schedule because you don't care about each competitor. You can look at how many tweets do all your competitors produce in each time slot, and this is what you care about. And these schedules are with respect to each producer, because you have a different set of competitors for each follower. In this case, there is a single competitor, so we can drop the second subscript, which makes the notation easy. So this is what we have before we even go and talk about scoring a schedule. So now, how are timelines constructed given this social network and these schedules? The process is as follows. In the first time slot, the producer first posts whatever number of posts, and then the competitors post. So the posts appear above the producer's post on the timeline. And then we move to the next time slot, and this process repeats. Okay? In this time slot, one of the users logs in and reads the timeline. So we don't know if the user reads the entire timeline, but they're going to read at most until this post. And then we move on with the next time slot, and then the next user comes and reads the timeline. So this is what user 0 sees in his or her Twitter window. This is the end of day 0. Then we move to the next day, and the process repeats. So what is the interesting thing that happens here is the user logs in again, but we assume now that the consumption is at most until a certain post. And why do we assume this? This is because in Twitter, they actually mark the point, the first post that you consumed on the previous login. So people know that I'm not going to scroll past this post because I've already seen this before. So there is a certain maximum depth that we can assume. Okay. And similarly for the next user, the user stops at a particular depth. So finally, what we have, this process repeats every day, and the view of each of these users is stable. And what we want to do is we want to score these views. So to help us score, let's define some notation which makes the formulation easier. So we consider sort of a grid of posts and a certain number of posts in each grid slot. And we need to find a way to link the social network and schedules there with the number of posts that the user sees on the timeline. And that is done via this pair of equations. Okay? Now that we have this, we can go and actually think about how do we score a timeline in a way that is proportional to attention. So the way we do this is we score each producer cluster. So there's a group of posts by the producer, which is what you care about. And how do we score each producer cluster? We break it up into the posts that are inside it, and we calculate an attention score for each post. And by summing them all up, you get your final attention potential. So now we're going to go and calculate the attention potential of a cluster. How does this happen? Let's say you have a cluster with X posts, and you have a single post at depth D plus D. So let's say there are D posts above this cluster. You want to go and score this, give this a score that's proportional to attention. So the attention we know is affected by two factors. The first is depth. So we define a function called the user survival function, which is basically the probability that the user scrolls past this depth in the timeline. So this is basically a decreasing function of depth. And using a parameter, you can control how information overloaded this user is. Then we define something called the cluster survival function, which is a decreasing function of the cluster size, because we know that large clusters negatively affect attention. So what we do is we go and we discount the score of a post by both of these functions. So now we have, you can consider this the probability that this post is given attention. So now we can go and we can sum the attention potential of each post and find the attention potential of a cluster. And that's how you come up with this equation. So the only missing piece left is you need a way to see what is D, what is Z ij, and you can define Z ij in terms of our previous notation. So now that we have the attention potential of a cluster, you want to find your objective function, and that is simply you sum over all clusters for all users, and that gives you the objective function that you want to maximize. So you can formulate the whole problem as a mathematical program. And if you look at what the objective function is doing here, it's trying to capture a balance. The balance is between the post volume. So you want your stuff to be read, so you need to post more. But at the same time, you're doing two things which affect you negatively. You're irritating users. You're also pushing down your own posts, which are lower on the timeline. Okay. So this mathematical program is actually an instance of the nonlinear and abstract problem. But in our case, our objective function is non-separable, and what this means is you cannot break it down into a sum of independent functions. It's also not concave, it's not quasi-concave. So it's in general, this problem is difficult to solve efficiently. So what we do is we adopt a local search algorithm, which is so it's essentially, you can think of it as greedy hill climbing. So you start with an initial schedule, and then you increment the number of posts in each slot until you arrive at some local maximum. So now, we've defined a formal model of attention. So how do we go and apply this to real data? If you were a producer, how would you apply the knowledge that we've given you? So we show you how to do this using a micro level experiment. Okay? So in this experiment, we take a single producer, and we take the producer with the most number of followers and tweets. We wanted a diverse follower population. We also wanted someone who has a lot of tweets, because this gives us some representative sample. We do two things. We first show you how do you estimate these behavioral parameters to because these are not things you cannot observe how irritated a user is or how overloaded the user is. And we also show you what is the attention potential that you obtain with different kinds of schedules. So let's first look at this user's follower and competitor activity. So there are a few interesting things you can observe. So the x-axis is time, the time of the day, and the y-axis is each follower. So you can see that there is, during lunchtime, this particular producer has reduced competition. We could use this in our scheduling algorithm, right? You also see that there are three regions of activity. There is a peak region where people are most active. There is a medium region, and there is a time when most people are not very active. So now let's go to how do we estimate behavioral parameters. So the first parameter is login time. We estimate the login time as the median start hour across all days. And what is a start hour? We assume a start hour is if a tweet has been sent after an inactive period of 8 hours, we assume that this is a login tweet. And we find the median of all these login hours, and this gives us the login time of each user. Then we go to the irritation parameter. How do we estimate this? So we adopt an observation by one of the surveys that we mentioned earlier. So the survey said that people get more irritated when they see frequent posts from weak ties. And tie strength is, in the social network analysis literature, tie strength is like something that's been studied often. And one common measure of tie strength is what is the probability of one person reacting to the other via likes or retweets or replies. So we measure this parameter as the strength of the tie between the producer and the follower. And we assume that, so we spoke about survival functions earlier, we assume a geometric survival, a cluster survival function. Then we go to information overload. So what we want, if we assume that you have geometric user survival, what we're trying to estimate is what is the probability that the user quits the timeline after each post. And we need to do this, we don't know exactly how people read their timelines, but we still need to estimate this. So the way we do this is, if we assume a geometric survival function, we know that the mean of this function is given by this equation. So we can actually we can estimate the mean from the data and then use this to find this parameter. So this is what we do in this case. So now we have all our behavioral parameters. We can actually go and estimate the attention potential over time. But to estimate the attention potential, you need a bunch of schedules. So we look at 4 schedules. 3 of them are baselines. The first is a very naive baseline. You post the same amount in each time slot. The second is the most. So this problem has been, there are a lot of heuristics that people use today to actually schedule their tweets. And this is the most popular heuristic. They say, let's look at the activity of all our followers and let's go and tweet when the activity is at the maximum. There is a second heuristic which people have recently started using, which they call post during the graveyard shift. So what they say is, at night, even though people are not visibly active, they are still reading their tweets. So let's go and post them. And then the final approach is our approach, where we run marginal allocation and we come up with a schedule. And now let's go and look at what is the attention potential that we obtain. So we have a heat map for each schedule, and these heat maps are, so they're normalized along the x-axis in each heat map. So the darkest green is the time of maximum attention that is obtained by this particular follower. So there are 2 things that two unusual things that you observe here. The first is that this does not correspond to activity times. So the attention potential that we have estimated happens to be the most at around midnight time, which is what the graveyard heuristic suggested that people go and try. So what our schedule actually finds is that it is better to go and post at midnight. Another thing that our schedule finds is that it's a good idea to go and post around lunchtime because that's the time of low competition. So in this scenario, it's easy to interpret because most of these users are in the same time zone. So you can actually go and construct these schedules by hand, by observing activity and using heuristics. But if you had users in different time zones and with different levels of irritation towards you, it's going to be extremely difficult to construct an optimal schedule by hand. And this is what we are able to go and perform on par with hand-constructed schedule. So to summarize, so we've taken the problem of timing and frequency, and we've studied it scientifically. And to do this, we looked at 3 factors that influence attention, and we validate one of them and we quantify them. We also link these factors with the actual attention obtained using a formal process. And finally, we go and we analyze our formalization on real data from Twitter. So future work, there are 2 directions that this can proceed. So interestingly, the monotony aversion that we introduce and quantify, this has connections to a number of domains which are unrelated. So the first is recommendation list diversity, which some people who are doing recommendation systems may know of. So what people say is, if you increase the diversity of your recommendation, it can also be used in consumer science, where there's a bunch of people who are studying why do users switch brands, why do users get bored of a particular brand. And recently there have been papers studying why do users reconsume certain items. So why do people listen to the same song many times and then stop and then listen to the same song again. So our formulation can actually go and guide research in a number of different domains. And the second line of future work is in the scheduling problem itself. So in one of the surveys they mentioned that irritation leads to unfollowing. So is there a way of extending this work, taking into account rating types? And the second direction is we are only considering an ego network. So we're considering a producer and all the followers of this producer. But each follower also spreads your post in a different way. So people have been studying influence maximization in this space. Is there a connection between, can we schedule to maximize the organic reach of my post? And then there are some direct extensions that we can do, which is we've discretized time. So is there a way of making this a continuous time process with multiple login slots? And we have assumed a particular survival function in our case. We've taken the most simple survival function. We don't know which survival function works best in which social network scenario. So one direction would be to figure out how do we go and implement this in different social networks. So as Panos mentioned, we have a submission KDD, we have a patent, and we also started sort of commercializing this with the help of KAUST's incubation center. And any supplementary material is available on our website. That's it.